Okay, yes. So thank you very much for the introduction and the invitation. I'm very happy to speak in this seminar. So today we'll talk about two notions as in the title, heaviness and the relative symplectic cohomology. This is based on joint work with C.Y.Mak and U.Varolgunes. So let's fix the symplectic manifold and talk about the symplectic rigidity. So usually those symplectic rigidity is captured by the Hamiltonian displacement. So suppose we have a compact set K in our symplectic manifold M, and it is called Hamiltonian non-displaceable if it cannot be separated from itself by any Hamiltonian diffeomorphisms. And let's look at this basic example on the two torus, which we will revisit this example often in this talk. So we have these two torus. We have there are three types of circles on the torus. So the orange one, we can displace it away. So we say it's not rigid. And there are red circles and pink circles, which are not contractible. They cannot be Hamiltonian displaced from itself. And we say those circles are rigid. This can be shown, for example, using Floer theory or other tools. And the interesting thing is that we have another layer of rigidity to consider the union of those two circles, this red one and this pink one. So as the set itself is not displaceable, however, it has the stronger rigidities such that those rigid circles cannot be displaced from this union. However, those rigid circles, for example, we could have two parallel those pink circles. They are they could be pairwisely disjoint. Each of them itself is non-displaceable, but somehow they don't talk with they don't talk with each other. So the third layer of rigidity, sometimes called superrigidity, is that there are some sets which somehow see all the rigid objects. So this is our first example. So this phenomenon happens in somehow general settings for any symplectic manifolds, and now we have several languages to describe such a phenomenon. So according to Entov-Polterovich, this is called the hierarchies of rigid sets. So now here I list the four types of somehow languages to describe those phenomena, and I will not define those notions, all of those notions precisely, but only touch upon some of them. So maybe the earliest, somehow the earliest one is the first one is around 2000 or even before 2000. And the main character of today is this language by using spectral invariance introduced by Entov and Polterovich called heavy and super heavy sets. This is around 2008. And those two middle ones are more recent invariants, I think, after maybe 2018, after the invention of the relative symplectic cohomology. in Varolgunes thesis. So we have those 4 different theories, not very different theories, but they share some common good features. So the first one is rigid sets are Hamiltonian non-displaceable, so we call them rigid, and we have some other sets called super rigid. So super rigid sets are rigid, but in general, not vice versa. So it doesn't, not every rigid object is super rigid. Somehow, the third property is that any rigid set must intersect this super rigid set. So this is several layers of rigidity, and sometimes it's called hierarchies of rigid sets. So another remark is that those first three, so all of those 4 things are defined by using floor theory. So using floor theory. And the first 3 is defined by using closed string version. In other words, Hamiltonian floor. So the last one is by using Lagrangian floor. So they share some common features, so it's natural to ask some comparison between them. So today our main task is compare those 2 notions. So these are some names who invented those 4 language. Some of them I will give the precise definition later. So maybe one of the important relations between the 4th one and the first one is well studied. I summarize it in the following theorem due to many people in different generality. So Albert, Biran, Cornea, Entov-Polterovich, Bukaya, Otono. Suppose we have a Lagrangian submanifold. I say it is good if it's a Lagrangian floor, self-Lagrangian floor homology is well defined. Then the theorem says if this Lagrangian floor is non-zero, then it is a heavy set in the sense of Entov-Polterovich. So this, in some sense, is the implication from this item to that atom. So today, our goal is to establish some equivalence between these 2, heaviness and ACH visible, which I'll introduce later. And as an application, once the relation between these 2 are known, then we have some partial result relating those other items. If time permits, maybe I can also say something about other things. Okay. So the main theorem is the following. For a general compact set K inside of closed symplectic manifold M, so K is heavy if and only if some invariant, which is called the relative symplectic cohomology, is non-zero. So I'll define those items precisely later. So this is the main theorem. And some quick comment about the statement is that this is an if and only if. First, it is an if and only if statement. Therefore, it's somehow a full characterization of this heaviness. So compared with the above theorem, is in some cases one have this one-way implication, but in this case, I think since both of these 2 invariants are defined by Hamiltonian floor, it's reasonable to have a if and only if statement. Another good thing is that this works for any compact set K. So we don't require any regularity regularity of this set. We don't need it to be a manifold or Lagrangian and so on. So that's the statement. So of course, since we work on general symplectic manifold to define Hamiltonian floor theory, one need to assume the virtual techniques. But the construction in our proof is roughly about estimating actions of periodic orbits, so it's somehow orthogonal to those regularity of moduli spaces. So this another remark. So so far, any question about the statement, the theorem? Okay, so now I will just define those two notions, heaviness and relative symplectic cohomology. So heaviness is defined by Entov-Polterovich in terms of spectral invariance. Spectral invariance is kind of critical values of Hamiltonian floor groups. So I briefly recall the background here to fix the notations. So suppose we have some non-degenerate Hamiltonian function H. We can form a complex, chain complex CFH. The generators are kept one periodic orbits. So we have a periodic orbit gamma. We equipped it with a capping U, and we modulo some relations. The differentials counts floor cylinders connecting those capped orbits. And I just want to mention our convention on action function, though, is the integral of the Hamiltonian over the orbit and plus the integral of symplectic form over the capping. So both are positive signs. And our differential increase the action and the degree of these generators. So that is, we have a cohomology co-grading and the action filtration is going upward. Then we can use this PSS isomorphism to define spectral invariance. So we have an isomorphism between the quantum cohomology to the Hamiltonian floor. And the spectral invariance CAH is a function of two variables. One variable is this a class in quantum cohomology A. The other variable is the Hamiltonian. And it is defined as the largest action of X, such that X is some chain level representative of this class PSS of A. So that is, we fix this class PSS of A. Then we look for the largest action of its chain level representatives. This is defined as the spectral invariance of A and H. So it has lots of good properties and form an active research field in symplectic topology. And Entov-Polterovich used the spectral invariance to define heavy and super heaviness. So today I'll only focus on the heavy part. The definition is the following. So a compact set K, again, is inside of M. A compact set K in M is called heavy if for any H, which is non-negative, such that it is 0 on K, then C1H is 0. So here 1 is the unit of quantum cohomology. So that is, suppose we have this is our compact set K, then we need to consider those Hamiltonian functions, which is 0 on K and globally is non-negative, and we calculate the spectral invariant. If C1 of H equals 0 for any such H, then this compact set K is called heavy. So that's the definition of heaviness. So roughly speaking, this function H may have lots of generators, let's say some orbits here, some orbits here. Then they have different actions. So the heaviness is saying that if, for example, if we have some orbits in the very high level with some positive action, then we don't want it to represent the TSS image of the unit class. So somehow we only allow those orbits with 0 action representing this unit. So that's the definition of heaviness. So this is a remark is that this is not the original definition. The original definition, due to Entov-Polterovich, used the homogenized spectral invariant. But in this spectral setting, we can apply some trick to only study this Euro spectral invariant by study C1 of H. And another remark is that during this talk, when I say heavy, I always mean heavy with respect to the unit. In general, they also define the heaviness with respect to any idempotent. But for simplicity, I will just restrict it to the unit case. So that's the definition of heaviness. So now, the second part about the other side, relative symplectic cohomology, is defined by U.Varolgunes in his thesis. So this will be a algebra over some field. So the field is called the universal Novikov field, similar to the formal power series, but we allow those powers to be real numbers. So here we have those formal sums, AI times t to the lambda I, where AIs are rational numbers, AI are real numbers, and we require it goes to positive infinity. So this is the background field. And how do we define this relative invariant is we start with a K, so start a compact set K inside of M. This relative invariant is also a kind of Hamiltonian floor theory. However, it's not of a single Hamiltonian, but of a family or a sequence of Hamiltonian functions. Suppose we have a sequence of Hamiltonian functions. Let's assume they are non-degenerate and they are monotone, which means they are increasing, such that they satisfy the following conditions. They converge to 0 on K and diverge to positive infinity outside of K. So in this picture, suppose this is...
Sorry, increasing, you mean pointwise?
Yes, pointwise increase, yes.
Thank you.
So suppose in this picture, this is our compact set K, and on the compact set K is always negative, however, increasing to 0. And outside of those, outside of K, we assume it diverges to infinity. So that's given those Hamiltonian functions, we could form those Hamiltonian floor complexes For each of them, I have CFHN, CFHN plus 1. So let me remark that in the second part, we slightly changed the definition of the Hamiltonian Floer complexes. Previously, the generators are kept orbits, but in this convention, those things are generated by just orbits. So those are, let's say, CFH are just generated by orbits over this lambda field. So it's somehow lambda times gamma, where gamma are the one periodic orbits of those functions. And in that case, we don't have a action since we don't have cappings, but we have a valuation coming from this background field lambda. So somehow we define the valuation of a term as a gamma times t to the e is defined as just this number e. So in other words, in this setting, the generator, the periodic orbits doesn't carry any action or valuation, or the valuation is 0. All the valuation is coming from the coefficient field. And to make this work, we need to also weight the Floer differentials by some energy. Suppose we have a Floer differential connecting gamma minus and gamma plus, then its contribution in the differential is gamma minus goes to gamma plus times t to the some power, and this power is given by this energy. Integral of omega plus the integral of h on the positive end minus the integral of h on the negative end. So if we have a fixed Hamiltonian, then this number is just the action difference. But if we have suppose we consider the continuation maps, then this number is always non-negative since we assume this monotonicity. So suppose we have these continuation maps by filling in those Hamiltonians of one parameter families to connect Hn to Hn plus 1. By using this monotonicity, we can make this number to be non-negative. Then we can define those Floer differentials, Floer continuation maps, those in, but weighted by some powers of t. So then we have the sequence of Hamiltonian complexes. So the usual way to make a invariant is, for example, due to Viterbo, is by taking the direct limit of this sequence of complexes. So here we can do the same thing, but we will use another algebraic model, which is called telescope. This telescope is quasi-isomorphic to taking the direct limit, but somehow algebraically is easier to handle to prove some algebraic properties. So how it is defined? So the telescope of this sequence of complexes, so in the chain level is just a big direct sum. So for each CFHN, we have two copies of them. One shifted, the degree shifted by 1, and we just direct sum all of those together. So in the picture is that we have this sequence of Hamiltonian Floer complexes, and from each of them we have two copies here. And they are connected by these continuation maps. So the differentials are just the sums of those operators. So more explicitly, suppose we have an element x1 here, x1 prime here, x2 here, x2 prime here, and so on. The differential, the big differential is just taking the derivative, I'm sorry, the d1 of x1 and the plus x1 prime. So that's the first slot. In the second slot is just d1 times d1 of x1 prime. And the third slot is we have three arrows here. So d2x2 plus h1 x1 prime plus x1 prime, x2 prime. That's the third slot. So this is a big differential, but let me mention that I'm omitting all the signs here. So actually, those things should be with positive or minus signs in order to this differential square to be 0. But let me pretend all of them have positive sign. So that's the telescope. The telescope, as we mentioned, is quasi-isomorphic to the direct limit. So we can take the homology of this big complex. However, here we want to take one more step. We take the completion of this big complex before taking the homology. Otherwise, I think this invariance is always isomorphic to this quantum cohomology, since each of them you have an isomorphism. So the completion is, again, nothing very fancy. It's just by allowing infinite sums. So that is saying, previously we have this direct sum, which only allow finite sums of combinations of orbits generators. Now we allow infinite sums like the sum of xi times t to the lambda I. But we need to require that those powers t weights going to infinity. So that is, we allow infinite sums with the valuations going to infinity. Then after the completion, we take the homology to get this invariant, which we call the relative symplectic cohomology of K inside of M. So it's just the homology of this completed telescope. So that's the definition of the relative invariant it's constructed in Varolgunes thesis. And it has several, yes.
So when you say this is quasi-isomorphic to just taking the direct limit, like in Viterbo's original approach, that's so the complex is the complex, and its cohomology is quasi-isom is the same. I mean, could you maybe explain something?
So yes, so what I'm saying is just telescope of CFHN. Those big complex, the homology of it equals h of direct limit and goes to infinity CFH. So that's what I mean. Yes.
Thank you.
So that is saying, yes, in this sense, if we don't take completion, we have this isomorphism, and we know this direct limit, again, this direct limit commute with homology. So we have limit h of CFHN. So we just, however, we know each of them is somehow a fixed thing. Then we take direct limit. It's not a big change. So, but later we will see if we take the completion, the answer might be very different from the quantum cohomology.
But just building off the previous question,
yes.
Did that isomorphism of homology is induced by a morphism of chains or not?
You mean this quasi-isomorphism?
Yes, that isomorphism. When you say quasi-isomorphism, there is a morphism of chains underlying it.
Yes, let me remember the argument. is so I think the argument was after a finite truncation. So that is, suppose we just stop at some hn. So say we stop at h3, then there is some map from this thing to CFH3. And one can prove this is a quasi-isomorphism. Then I think they use the direct limit of quasi-isomorphisms is a quasi-isomorphism, something like that.
Okay, thanks.
Yep. So this was defined in Varolgunes thesis. And it has some good properties which enables us to study this rigidity phenomenon. In particular, Konkonov-Varolgunes make the following definition. K is called SH visible if this invariant is non-zero. And K is called SH full if this invariant is zero for any K prime doesn't intersect K. So that is, let's say we have a big symplectic manifold M here, I have K here. And if K is called SH4 if any K prime outside of K has vanishing invariant. So that's the two definitions. And the good properties are, first, the non-vanishing implies that K is non-displaceable, and actually one can prove is not stably non-displaceable. And this invariant satisfies some Hamiltonian invariance, so SH K equals SHM VK. So then you can, study this Hamiltonian displacement. And the second definition you can see from the definition is somehow try to mimic this rigidity and super rigidity properties. Just make an SH4 set K must intersect any SH visible set. So that's the two definitions. And maybe I should mention two examples of this calculation, why this invariant somehow is interesting or is different than the quantum cohomology. So first, SH, the empty set is zero. But in particular, by the first, by this property, this stably non-displaceable property, any displaceable set has vanishing relative invariant, and we have a global section SHM of this. If we take M to be the compact set itself, then this is quantum cohomology of M. So that's two somehow extremal cases. Another way of thinking this is that we have this symplectic manifold M. We have lots of, say, compact set K's here. And this relative invariant tells us some assignment of the quantum cohomology into each pieces. So quantum cohomology of M. So somehow assignment to each piece, somehow to each piece we have algebra, and globally it's just the quantum cohomology itself, and for a very tiny part is just zero. This philosophy further developed by Dikstein, Ganor, Polterovich, Zapolsky. They defined those quantum cohomology valued, ideal valued quantum measure by using a variant of those invariant. Therefore, they can really associate each compact set with some ideals in the quantum cohomology. But if I have time, I can say some connections between this work and their work. So that's the definition of the relative invariant. So any other questions? Okay, so now, before doing the proof of the main theorem, let's first see some applications. So recall our goal is to show, or the main theorem says that SHMK lambda non-zero if and non-zero if and only if K heavy. So that's the main theorem. So now let's see, suppose we have this equivalence, what can we do? So the main strategy is by using this equivalence to study both sides. In other words, we can use the tool on one side to study the other side. So on the side of relative symplectic cohomology, besides the previously mentioned property, there are two non-trivial, main properties. One is called the Meyer-Virtuosi sequence. The other called the interpolation invariance, which I will recall them later. On the side of spectral invariance, there is huge active research field since 2000. So the rough idea is to just use the tools on each side to study the other side. And I will present some sample example or corollaries in the following. And we expect there should be more once this is more, let's say, well understood. So the first corollary is a direct consequence of this Meyer-Virtuosi sequence. So suppose we have two disjoint sets, and they are not heavy. Each of them are not heavy. Then their union is not heavy. So that's a first corollary. The proof follows the Meyer-Virtuosi sequence. Suppose we have K1, K2, and under good conditions, for example, disjoint is a good condition. Under good conditions, we have this Meyer-Virtuosi sequence connecting the invariant of K1 union K2, the invariant of K1, direct sum of the invariant of K2, and their intersection. So in this case, their intersection is empty, so we have this is 0. And suppose we know K1 and K2 are not heavy. So this is 0, which means this is 0, this is 0. So we immediately get the relative invariant of their union is 0, which says that the union is not heavy. So this somehow seems just directly follows the Meyer-Virtuosi sequence, but we are not sure whether there is a pure spectral invariant proof of this statement. Actually, this somehow related some formula like this. Suppose we have K1 here, have K2 here. Then in order to study K1 is heavy, we need to study Hamiltonian function like this. For K2, we need to study Hamiltonian function like this. For their union, we need to study Hamiltonian function like this. So that is saying how the spectral invariant of these three Hamiltonian are related. Just in terms of the spectral invariant, people are asking for such a formula for example, the sum formula or the Meyer-Virtuosi formula for the Hamiltonian functions. So this relative invariant in some sense provide a way to study such phenomena. So that's the first corollary. The second corollary is a generalization of these two torus example to any Calabi-Yau manifold. So by Calabi-Yau manifold, I just mean a close the symplectic manifold with the C1, the first chain class of the tangent bundle is 0. Then what can we do with this manifold is the following. Suppose we have this manifold, we can take a smooth symplectic hypersurface D inside of M, such that it represents the symplectic form by some positive multiple. Then we throw away this D, we get an open manifold. And this open manifold, one can construct a Liouville structure on it. So that is, we have this manifold M, we throw away this D, the open manifold is somehow Liouville domain. Then we can apply this inverse Liouville flow to find its skeleton, which I call LD. So the skeleton is just somehow I mean, you apply the inverse Liouville flow, the stable point of those Liouville flows. And the interpolation invariance I mentioned earlier is the following. Suppose we want to consider our K is just a neighborhood of D. So let me use another color. So say this is our K. Somehow not very visible. Suppose this is our K. Then initially it's just a tubular neighborhood of this D, and one can show this D is stably displaceable, so this K has vanishing invariant, relative invariant. The interpolation invariance is that it's saying that under this reverse Liouville flow, we can just enlarge K, enlarge K, enlarge K. The relative invariant doesn't change. So this is the interpolation invariance. In other words, it's an interpolation between those Liouville domains. However, in this case, the complement of those Liouville domains. So therefore, we know for any compact set K which is away from the skeleton, it must be inside of some those enlargement, which has vanishing relative symplectic cohomology. So therefore, we can show that combined with the previous criterion on Lagrangian floor, we can show that any floor essential Lagrangian L must intersect the skeleton D. Since floor essential means that the self-floor cohomology is non-zero, by the previous theorem says it is heavy. Heavy implies that it has non-vanishing invariant, and which contradicts the following argument. If it's away from this skeleton of D, it must have zero relative invariant. So that's the generalization of this two torus example, where you can think this two torus, you take the divisor as a single point, then the skeleton is just this union of two circles. So you shrink this neighborhood of this divisor. Then they say we have a general analog in Calabi-Yau setting in higher dimensional case. So that's a second corollary. Okay, so any questions about these two applications? Okay, so I have some other applications, but seems out of time. So let me skip those applications and go into the proof, some sketch of the proofs. So recall our goal is to show SH and K non-zero implies is equivalent to heaviness, but in practice is more convenient to prove is counterpositive. So this is zero if and only if not heavy. So first, let's consider this direction. Suppose this relative invariant vanishes. Then what can we say about this compact set? As we mentioned, this big telescope model, the differentials of these telescopes contains all the continuation maps. So therefore, we can just look at those the differential in this telescope to get useful information from the continuation maps. So let's pick a special element of the following form. So recall our telescope is of the following form. We have a direct sum of all of these things, and we have differentials like this. Now we just pick a single element y1, 0, 0, 0, which means y1 lives in here and other places are just 0. So y1 is an element in the Hamiltonian floor complex. We assume it's closed. Then we can see in the telescope is also closed. By our assumption, the relative invariant vanishes, so it must be also exact. So there exists some primitive of this y1. And suppose x1, x1 prime, x2, x prime is a primitive of this y1. Then we get the following sequence of differential equations. So in the first slot, we have this one, second slot with this one. Then what does it say? So these two equations tells us x1 prime is closed and homologous to y1 since it's up to some exact part. Then similarly, the second and the third and the fourth equation says that x2 is also closed and homologous to h1 x1 prime, where h1 is this continuation map. Then we have a sequence of those relations. The first relation happens in the first Hamiltonian floor. The second relation happens in second, and so on. So on the other hand, we know that those continuation maps is compatible with the PSS map in the sense that we have those lots of PSS maps from the quantum cohomology to the first one, to the second one, to the third one. In the homology level, it commutes with these continuation maps by a gluing argument. So that is those triangles somehow commutes. Then we use this factor to see that suppose y1 represents some class, then x1 prime represents the same class. x2 actually will represent its image under continuation maps. So we get if y1 represents PSS1 of some class, then x2 prime should represent PSS2 of the same class, and x3 represents PSS3 of A, and so on. Then we have a sequence of elements represents, so xn prime represents PSSn of A. So we have a sequence of chain level representatives of this PSSNA. So the last step is to apply this convergence. So recall that we are not allowing arbitrary infinite sums. It is allowed only when the valuation going to infinity. So that is, moreover, we have the valuations of this xn prime going to infinity. So in conclusion, we arrived at the following proposition. If we have the relative invariant is vanishing, then CA of Hn is unbounded, since this valuation of those, already we have a sequence of chain level representatives going to infinity, where Hns are the functions we used in the construction of the relative invariant. Then this would imply that if this vanishes, then K is not heavy, since these Hns can be very close to those functions of the type which is 0 on K and somehow positive outside. And heavy is saying C1 of those functions should be 0, which contradicts to the unbounded of those spectral invariants. So that's the one direction. Vanishing of the relative invariant implies K not heavy. So this more or less only relies on the definition of the telescope model. So the upshot is the differentials of the whole telescope already contains all the continuation maps. Therefore, by looking at this telescope, you can get the information of those continuation maps, which is enough for our purpose here. Okay. So in the last several minutes, let me sketch the proof of the other direction. So the other direction is H and K lambda equals 0. The other direction is not heavy, implies that. So the other direction is somehow more technical. It needs a chain level product structure of this relative invariant. Recently, this chain level product structure is constructed by Abzaid, and Uvarolgunes. So previously, we only say this homology is algebra and it has a product structure, has a unit, and so on. And recently, they upgrade the thing in the chain level. They construct some chain model of this. I mean, a priori is different than this telescope model, is somehow other model, which has a chain level product structure. So we will use the result as a black box. Actually, we only use a very small part of it. In general, they also construct those infinity structures, and we only use this product structure, i.e. the first two infinity structures. So the proof, I would like to summarize it in the abstract setting. Since I feel this abstract setting is somehow general, one can also apply this abstract proof into other theories, in particular for Lagrangian floor. So in the Lagrangian floor setting, we already know there is a chain level A infinity algebra under some conditions. And somehow this Lagrangian setting also satisfies this abstract formalism. So therefore, I expect maybe there are also applications in the Lagrangian side. So now let me say this abstract setting. Suppose we have a chain complex, let's say over this universal Novikov ring, and we assume it's complete. And probably we need to assume it's free or quotient free. Let's say free. So it's just a vector space. equipped with a product structure in the chain level, we also need to assume this chain level product structure somehow only increase the valuation. So valuation of A times B somehow is greater than valuation of A plus B. So this is somehow a compatibility with this T parameter. And we assume it satisfies this graded Leibniz rule. And this chain level product structure recovering the homology level structure. So if the unit admits a chain level representative with positive valuation, then the unit vanishes in the homology level. So that's a conclusion. Conclusion is here. If we have some chain level representative with positive valuation, then the unit vanishes in homology. In particular, the whole homology vanishes since the unit vanishes. So what's the proof? The proof is a pure algebraic or combinatoric algebraic argument. So suppose we have this X, which is a chain level representative of the unit with a positive valuation. Then we can just multiply X with itself. So X times X, we know, is also homologous to X since unit times unit is unit. So their difference is dy, some exact element. And we can keep multiplying X on the both sides of this equation from left. So we get the second equation. By the graded Leibniz rule, I have d of X times Y. Again, here I'm omitting those positive negative signs. Then we can keep doing that. We have a sequence of equations. The last step is just formally add them up. So formally, the left-hand side, you can see lots of cancellation happens. What left is just X, and the right-hand side is d of infinite sum. So in order for this infinite sum to be convergent, we need to use that the valuation of X is positive. Therefore, the valuation of the nth term going to infinity. So this is somehow crucial. If X has 0 or negative valuation, we do have this formal primitive of X, but is not a convergent element. So that's how we construct the primitive of the unit by using this positive valuation X. So maybe another remark is that here the notation X to the, for example, X to the 3 is actually, strictly speaking, I should write it as X times X times X, since we do not need to assume those product structure is associative. For example, in this infinity algebra language, those product is somehow not associative, but up to some homotopy terms. However, in this argument, we don't assume this associative. So everything we just multiply from the left. So that's somehow the convention. So therefore, this Lagrangian setting, I think, also fits inside to this algebraic setting. So finally, how do we use this algebraic lemma to finish the proof? So suppose K is not heavy, then we have some function which is roughly 0 on K and positive outside of K, and such that C1 of, we have a chain level representative of the unit which has positive valuation. So that's somehow the definition of heaviness, which we used before. So this uses C1, H1 greater than 0. Then the last two steps is to use this H1 to push it into this algebraic model those people constructed to construct the X, which represents the unit and has positive valuation. Then the above algebraic lemma says this invariant vanishes. So that's the whole proof. I think I'm on the time, so I'll stop here. Yeah. Thank you.
Thank you very much.
Thank you. Yes, I apologize for being very technical. Yeah.
No, this was great. Thank you. Questions?
Yes, yes. Go ahead. Yes.
Yes,
So,
Chris,
sorry,
please.
yeah, sorry, Yuhan, they're cutting down a tree outside, so I don't know if you can hear me or not. But can you go back to the applications and just go over
Right.
the last couple of things that you didn't have time to say?
Yes, thank you. Okay, so the last corollary is about involutive maps. So suppose we have a map from M to R to the N. We say it's involutive if for any f G maps from R to the N to R, and we have F composed with phi, G composed of phi. Those two functions are functions on M. And the involutive means all of those functions has vanishing Poisson bracket. And the corollary says that any such map has at least one heavy fiber. So this answers a question by Entov. So let me mention that, for example, those involutive maps happens a lot. I mean, in this happens a lot in these torus fibrations and integrable systems. And the remarkable thing or application of these heavy and super heavy sets by Entov-Polterovich is that they prove that any such map has at least one displaceable fiber, non-displaceable fiber by Entov-Polterovich. Then further, Entov asked the question whether this should be strengthened to be a heavy fiber in his ICM talk, and the answer is yes. So the argument is the following: suppose we have this M, and it maps to some region in Rn, is some compact region. Then suppose on the contrary, we don't have any heavy fiber. Then since this heaviness is defined by spectral invariant is in some sense continuous, then for each point we have a small neighborhood such that the pre-image is also not heavy. Then we have a cover of M by non-heavy regions. And this involutive thing or the Poisson commutative property enable us to play a game of this Meyer-Virtorius game for multiple sets. Then, since each piece, it has vanishing invariant. So each piece has zero invariant. We could not put together to recover the quantum cohomology. So that's the contradiction. So that's the proof. And I think if you look into this original proof of Entov-Polterovich, why could they do this non-displaceable setting instead of heavy setting? Somehow the thing missing is similar to the corollary one. For those heavy sets, there is no, at that time, there is no proper Meyer-Virtorius formula. But in the language of this relative invariant, there is a Meyer-Virtorius formula, then all the argument works. Yes.
You need some special assumptions for the Meyer-Virtorius, right?
Yes, yes. So in this case, these assumptions is satisfied by this involutive map, such that those pre-images are somehow Poisson commutative. Then they fix into this somehow a more advanced condition for this Meyer-Virtorius. So previously we only use that they do not intersect or their boundary do not intersect. But a stronger conclusion is that if their boundary has some Poisson commutativity, then that's also true. So that's yeah.
But doesn't it have to be cut up by something polyhedral or something like that? Or okay, maybe I don't remember the exact statement. So okay.
No, that's I mean Varolgunes had even kind of more general assumption, which is slightly less geometric, but anything which comes from this involutive sets is good.
Okay, thank you.
So it's kind of Poisson commuting. I mean, it should be remembered as Poisson commuting sets, whatever this means.
Thank you.
Thank you. Yeah, that's also my impression. This involutive setting is sufficient enough for his general Weber-Torres argument. Yes.
One question.
Well, in this table which you showed to us at the very beginning, so there was this remarkable line number 4, namely about kind of some counterparts of the story within Fukaya category.
Mm-hmm.
Could you please comment about this? Because
yes. So now let me just swipe. I'm sorry. Okay. So now we have this arrow is by this open close map by many people. We know this non-trivial Lagrangian floor implies heavy, and it's also natural to ask what's the analog in the super heavy setting. I mean, one could expect some thing could be done in the following argument. So suppose you have a collection of Lagrangians. They satisfy some kinds of those generating criterion, and the union of this collection should be super heavy. So I mean, I'm being very rough here, but that's somehow the idea. So the possible proof is the following. So for a collection of Lagrangians, assume we have this infinity algebra, those some all defined, one can study the Hochschild cohomology of this collection. Then the generating criterion is saying that this image of this quantum cohomology lies inside of the open close map in this Hochschild cohomology. Then I think probably one can also define a spectral invariant of those Hochschild cohomology. In other words, for a single Lagrangian L, say we have HFL, there are open string spectral invariant by Lerchik with Laposi and so on. But suppose if we have a bunch of them, how do we define somehow multi-version of spectral invariant incorporating different Hamiltonians? That's one possible direction. The other direction is to ask whether the opposite implication is true. So if a priori, if we by any chance we know the Lagrangian is heavy, we ask whether it has non-zero Floer cohomology. So in general, I don't know whether this is true in general, but this, by using the second language, one can think the following. So we have this HF of L. We also have SHM of L. So just view L as a compact set itself. Then this opposite direction is asking whether those two things are the same. So if they are the same, then I think the other direction is also true. But in general, I don't know whether those two things are the same. Since one thing is the left-hand side is open string, the right-hand side is closed string. So in general, I don't know. So that's one thing we can also consider about. So the non-vanishing of this one implies the non-vanishing of that one, but in the opposite direction, I don't know. That's something I'm not sure. Yes.
Can I ask a question?
Yes, yes.
So here, you say like, is it possible that the relative symplectic cohomology of this SHML is like the partial cohomology of the HF of L regarded as an algebra?
If I mean, that's also a good question. I think if L is exact, then probably that's, or L doesn't bound any disk, that's true, maybe. But I mean, let me make some further comment of this. The difficult thing is that suppose we have this L, and in order to define this thing, we're using Hamiltonians which are roughly zero on L and positive outside. So there might be generators outside of L. So if we can exclude those generators, only have those generators down on the L, then this thing is somehow related to just the Euro-symplectic cohomology of the cotangent bundle, but maybe with deformations. Then this is more, I would say, have more chance to relate it with the Hochschild homology of the loop space of the L itself. But in general, there might be outside of generators. So in theory, even the underlying complex, you have more generators. So I don't know. So in general, I don't know.
Okay, thanks.